particle physics excellence center in Amsterdam, or GRAPPA. She has received many awards and honors, partly as a member of the LIGO and Virgo collaboration. She obtained the Gruber Prize in Cosmology in 2016 and a Special Breakthrough Prize in Fundamental Physics also in 2016. And more recently in 2020, she obtained herself alone the 2020 New Horizon in Physics Prize for the development of novel techniques to extract fundamental physics from astronomical data. So Samaya is an expert in and has shown her abilities to combine information coming from different channels, from different messenger, we call them. That is, how to use both electromagnetic and gravitational wave signals to understand the dynamics, for instance, of binary neutron stars. And I think that's exactly what she will be talking about today with a talk, New Perspectives onto the Universe in the Era of Multi-Messenger Astrophysics. Samaya, the stage is yours. Thank you for being with us.
Thank you very much, and good afternoon, everyone, and also good morning, I guess, wherever you are in the world. Thank you, Luciano, for that extremely kind introduction. Indeed, I did meet you as a postmaster student in Paris. Can you hear me? Is this okay?
Yes.
Yes. And also, can you see my slides?
Yes.
Okay, perfect. I'm going to switch my video off just for Wi-Fi stability, but I am here, and so I hope you can see me now, and I will begin my talk. So just wait, stop the video. Okay, so yes, so the discovery of gravitational waves from a pair or a binary black hole merger in 2015, which was the most luminous event that we had observed in the universe at the time, has literally shaken and transformed modern astronomy, astrophysics, and physics. And there is this new spectral window, the gravitational wave spectrum, that is now accessible to us to probe the universe. And similar to the discovery of the entire electromagnetic spectrum in terms of viewing the universe, it is allowing us to probe new physical regimes and properties. Now, it's the multi-messenger combination of gravitational waves together with the electromagnetic radiation, as well as other particles, that is providing us with an immense source of astrophysical information. However, this comes with many challenges that I will discuss in my talk. Number one, analyzing and interpreting these gravitational wave signals themselves. Two, gathering real-time multi-wavelength electromagnetic data sets. And thirdly, interpreting these multi-messenger data sets and observations jointly. So in the past 7 years, during 3 science runs, we have now observed at least 90 black hole or neutron star mergers in gravitational waves with the LIGO and Virgo detectors. Now shown here is a schema where the vertical axis here denotes the masses in solar masses. The horizontal axis doesn't actually have any significance. And the blue bubbles that you see here represent the progenitor and the remnant or the final black holes observed. And the orange bubbles, what are most likely believed to be neutron stars observed in gravitational waves. Now shown by the purple and the yellow bubbles are the previously inferred black hole and neutron star masses that we knew previously from X-ray and radio measurements. Now there are several points to note that I'd like to underline. Number one, we're really uncovering a diversity in the fundamental properties of these black holes and neutron stars. Here we're showing the mass, and folding in observational selection effects. These indicate a broad distribution of masses, with some systems showing some asymmetry in their masses. Number two, several open questions remain to the nature of the remnant, as well as the progenitors. So you can see these by these mixed bubbles of blue and orange, and the existence of previously hypothesized mass gaps that we thought we wouldn't find these objects existing in. And thirdly, as these have been really the focus of my research in the past 15 odd years, I'll be focusing on these several events that you can see in the white box here, which we believe are neutron-star or neutron-star black hole mergers, systems where at least one of the objects has matter in the form of a neutron star, and where we may expect electromagnetic emission to happen from the delayed matter outflows from the merge of the two compact objects. Okay, so as they merge, we expect there to be some delayed matter outflow, and it's this matter outflow that's responsible for the electromagnetic emission. And in particular, I'm going to zoom into this game-changing first binary neutron star merger, denoted GW170817, the numbers simply from the date of the discovery in gravitational waves, that was observed in gravitational waves and in every part of the electromagnetic spectrum. Okay, and this really allowed several firsts sort of breakthrough discoveries from this one event. And I have to just mention that this is the only event so far where we have both gravitational wave and electromagnetic emission. And so these comprise not only the first time we could see a binary neutron star detected in gravitational waves, as well as in every part of every wave band in the electromagnetic spectrum, but the first time we could actually pinpoint a gravitational wave event in the sky, the first discovery of a kilonova and one of the astrophysical sites of our process elements, the first association of a short gamma ray burst with a binary neutron star merger, as well as the first time we could actually use these systems to measure cosmological parameters such as the Hubble constant constraint, and I will come to this. So really this one event has allowed for many discoveries, and I'd really like to stress that these discoveries are really and were really made possible due to the tremendous advance in gravitational wave detectors, decades of hard work, as well as hundreds to thousands of people involved, as well as in time domain astronomy, computational astrophysics. And it's these advances that are really resulting in multi-messenger astrophysics traversing many different fields in astronomy and physics, and providing these new measurements. So I'm really going to focus in the talk about three areas: high energy astrophysics, nuclear physics, and cosmology. These are areas that I and my group are working in, but really just to I'd like to stress the broader framework of how this field is really impacting many, many other fields. And so I'll begin by talking about the physics behind gravitational wave observations. Part two, I will really try to address and introduce the multi-messenger discovery of this first binary neutron star merger. Secondly, talk about how we can do nuclear physics with multi-messenger astrophysics observations. And thirdly, how we can do cosmology, and end with perspectives. And I'd just like to stress that there are thousands of papers in particular about this one event. So my references really are a bare minimum, just in terms of the clarity of my slides, but really please do look for the numerous review articles as well as my own that will be coming up. And so I'll be talking about work that has been done by my group in Amsterdam, as well as many former members, as well as large and smaller collaborations on the gravitational wave and electromagnetic side. But I'm showing this really to show the breadth and I think the diversity of individuals, as well as collaborations, as well as the international spirit of this field. And so let's go to the physics. But before that, let's ask ourselves again, what is the driving motivation for understanding these compact objects? Well, we're interested in black holes as they are vacuum solutions of Einstein's field equations. They really represent the extremes of space-time curvature. They have no surface, just an event horizon that's separating information from the interior to the outside universe. And they are the most fundamental and simplest objects in the universe that you can think of. They're described, or at least astrophysical black holes are described entirely by two numbers, their mass and their spin. On the other hand, neutron stars on the left-hand side are the densest objects that we know of. Matter is essentially compressed to several times that of the nuclear density at their cores, where fundamental and nuclear physics breaks down. And what are gravitational waves themselves? Well, they're an intrinsic prediction of general relativity. They're perturbations in the fabric of space-time that travel at the speed of light. And the lowest order, most dominant radiation is given by the so-called Newtonian quadrupole formula here, where IIJ is the mass quadrupole moment. So essentially, they're sourced by accelerating quadrupole or asymmetric matter sources. And what I'd like to stress is that our observable in gravitational waves is given by this time-dependent gravitational, dimensionless gravitational wave strain h of t, okay, which has a 1 over distance to the source dependence. So this is why we can use these in some sense as to give us information about distances to the events. Gravitational waves themselves are unprecedented probes of the source's dynamical properties, and they are weakly interacting. So this, of course, has made their detection incredibly challenging and, of course, resulted in this sort of decades-long work on the experimental side. They have two polarizations, H plus and H cross, which essentially act as transverse tidal field on matter. So what you're seeing here in this blue slinky or this kind of digestive colon is essentially the action of a gravitational wave passing through a ring of freely floating test particles. Okay, and you can see the action hugely exaggerated of the two polarizations acting from the gravitational wave. And this is precisely this tidal stretching and squeezing, how kilohertz gravitational wave ground-based detectors are actually measuring gravitational waves. So we have actually now a network of gravitational wave detectors, these Michelson laser interferometers, the two LIGO detectors in the US, as well as Virgo, the mainly European detector in Pisa, Italy, GEO600 in Hanover. CAGRA just came online the month before the COVID lockdown in the Kamioka mine in Japan, as well as LIGO India. We are very hopeful that this will be operational in the next 5 years or so. And the real motivation, or one of the motivations for having a network of these detectors, is for multi-messenger astronomy, as I will discuss later on. But indeed, these detectors essentially measure a fractional change in the arm lengths, which are proportional to the gravitational wave strain. And you can imagine a sort of gravitational wave passing through this detector from top to bottom of the Earth, and there being essentially this, the detectors measuring a linear combination of this tidal stretching and squeezing of the arm lengths of the two polarizations weighted by the quadrupolar antenna function of the detectors. So I'd like to spend a couple of minutes thinking about what we can actually pull out of the gravitational wave signal in terms of information. Okay, so what I'm showing here is an example and the time frequency power spectrogram of this very first famous binary neutron star merger that was detected on August the 17th, 2017. And you can see the signal shown in yellow above the detector noise shown in blue. And this was our loudest and remains our loudest. The signal to noise ratio was 32, and our longest signal that we've seen so far, 100 seconds. Okay, but what I like to really stress is you can see this ever increasing frequency and amplitude, which we refer to as this chirp signal. And we can understand how this frequency increases and evolves by simply invoking at 0th order a Newtonian description of the inspiral using the loss in Newtonian orbital energy and equating it to that Newtonian quadrupole formula that I showed earlier. And within a few steps, you can arrive at an expression, which we call the frequency chirp, where F here is the gravitational wave frequency, which is a function of this curly M, which is simply a combination of the two masses, which are inspiraling, radiating gravitational waves, which are taking away energy and angular momentum from the system, and the frequency. So by measuring f dot, as well as the maximum frequency when the signal went out of band, we knew already within sort of the first half hour that we were most likely looking at a pair of neutron stars. Now, of course, in reality, we really want to extract a whole lot more information. So we need to have a far more accurate model of that wave strain, that h of t, than this Newtonian description. So broadly speaking, we call this the gravitational waveform, which comprises these three phases, the so-called in-spiral, the merger, and the post-merger or ring down, which are corresponding to the different phases in the compact object evolution. And there are a couple of things I'd like to point out. The in-spiral is driven by the chirp mass, as I've mentioned. The merger requires numerical relativity, where you are directly solving Einstein's field equations in strong gravity, as perturbative approximations are no longer valid. And the post-merger describes the settling down of the final remnant of the merger. The second thing I'd like to stress is that chirp frequency formula that I showed earlier. The detector sensitivity is more sensitive to a particular epoch of the waveform for different masses. So when we're talking about the neutron star, black hole systems that we are interested in terms of electromagnetic counterparts, we essentially observe thousands of the cycles of the in-spiral phase with the LIGO-Virgo detectors, okay, lasting a minute or so. The second thing, the in-spiral is modeled extremely accurately using the post-Newtonian approximation in general relativity, where the v here is the characteristic orbital velocity, c is the speed of light, and parameters such as the reduced mass appear in the gravitational wave phase at the next post-Newtonian order, and spin effects appear at higher post-Newtonian order, which can cause significant beating and modulation of the waveform. Now, for instance, one can also measure finite size effects that come into play at 5 post-Newtonian order, which depend on the internal structure of the body. So, for instance, a neutron star has some finite size to it. And this becomes important as the orbital separation approaches the body's sizes. So for neutron stars, the tidal field of the companion is going to induce a mass quadrupole moment and actually accelerate the coalescence. And the ratio of the induced quadrupole moment to the external tidal field is what we refer to as the tidal deformability or polarizability, where K2 here we refer to as the love number, which denotes the compressibility or the stiffness of the object, and R here is the radius of the neutron star. So essentially what you're doing is you're dumping energy into these moving tidal bulges, which are contributing to accelerating the kind of gravitational radiation. So by measuring the tidal deformability, we can actually therefore infer information about the nature of ultra-dense cold matter. Okay, so one key effort in the community is really to incorporate more physics into the waveform, higher order effects of the spin, the tidal deformability, mass ratios, non-circular orbits. Here is an example of how asymmetric spin systems can basically, or misaligned spins can cause this beating. And this will all impact how well we can actually pull out the individual parameters. So, with these waveforms actually in hand, where we have these gravitational waveforms, one can then go ahead and actually cross-correlate your detector output, this very noisy time series, with template banks of 10 to the 5, 10 to the 6 waveforms, and not only actually detect the signal by matched filtering, but also actually infer the parameters of the source. And so essentially one is explicitly mapping out posterior probability density functions using stochastic sampling methods such as Markov-Chain Monte Carlo or nested sampling. And shown here are the parameters that we can infer from the gravitational wave strain alone. The redshifted masses, the spins, the tidal deformability, which appear in the phase, as I mentioned, and degeneracies can exist. And importantly, also geometric properties, the inclination angle to the binary from where we are as an observer, the source position, where it is in the sky, as well as the distance, the luminosity distance. And here there also exist strong degeneracies impacting how well we can actually measure these systems. And one of the things to stress is that at the moment, depending on the complexity of the waveforms that we're using, the analysis can take, using MCMC, etc., can take a day to several weeks to a month's time scale. And of course, for follow-up by electromagnetic telescopes and other particle telescopes, what is imperative is actually getting precise and accurate information out as soon as possible. And therein lies a lot of excitement in the last years about incorporating machine learning to actually speed up the analysis by several orders of magnitude. So I'm going to now move on to the multi-messenger discovery of this first event, just to lay out the scene as well as the challenges that this event has revealed. And so when we talk about follow-up or by electromagnetic telescopes, it's very important just to focus on how well gravitational waves alone can actually localize the source. Now, gravitational wave interferometers, these L-shaped Michelson interferometers, are quadrupolar all-sky antennas. They have very poor angular sky resolution. And one must essentially rely on triangulation of the time of the arrival of the signals, as well as some information about the quadrupolar antenna function to the event. Now for GW170817, the first gravitational wave sky localization, along with a distance measure of 40 plus or minus 10 megaparsecs or so, was released 5 hours after the merger. A more refined map sent out 10.5 hours later. And by essentially cross-matching the gravitational wave volume, so the sky area plus the distance, with known galaxy catalogs, this resulted in the discovery of a 17.8 magnitude. This is a very, very bright blue flash in the optical that was seen at 10.8 hours, first by the SWOPE telescope in Las Campanas in Chile, followed by several independent detections in the subsequent hour. Okay, and it was located to this elliptical galaxy in NGC 4993. Now, what I want to stress is when we first saw that bright blue flash, we didn't actually know for certain it was our neutron star binary merger, okay, or the counterpart, the optical counterpart. And it was really the subsequent monitoring of the light curve as well as the spectra in the next week to 2 weeks that really suggested that it was unlike any other astronomical transient that we had ever studied before. And so, with the gravitational wave, as well as the gamma ray satellites, the Fermi and integral satellites, discovering a low luminosity GRB 1.7 seconds later, this event, GW170817, was observed by over 100 instruments with a slew of ground and space-based telescopes. So essentially, I think almost every ground or space-based telescope that could observe this event did try to observe it. And it involved over, and at least the multi-messenger discovery paper that sort of encapsulates those first few weeks, involved over 3,200 co-authors. Okay, and so for astronomy or for astrophysics, this is a huge, I mean, this I think was a sort of unprecedented number of co-authors. So what I'm showing here in the schema are the different bands. you can see, and the horizontal lines, it's quite a busy plot, but I'd like you to focus on the horizontal lines are when the detections in different wave bands happened. So 11 hours, I mentioned, we saw the optical, 12 hours, the infrared with the Gemini telescope, 15 hours, the UV with the Swift telescope in a space telescope, the X-rays at 9 days by the Chandra telescope, and 16 days later, the radio flash was observed by the VLA. And so essentially really every single wave band. And indeed, for this event, this is where I spend most of my time on this specific paper. I'm really leading the writing of the X-ray, the radio, and co-leading the UV-OIR follow-up. So it was really a tremendous experience on a very personal level, as well as really on a sort of international collaborative effort that sort of happened very organically after the trigger was first seen. Now, one question I get a lot of the time is, well, why have we not seen any other events? And specifically in the third science run in 2019, why have we not seen any electromagnetic emission associated with these events? So let's consider what happened. Well, there were 55 non-retracted alerts were sent out. 44 of those remained in the offline analysis. And of these original 55 alerts, 8 were related to binary neutron stars and 7 were neutron star black holes. Now, the median localization for all of these events, these neutron star black hole events, was 4,480 square degrees. Okay, compared to the 30 square degrees I mentioned for GW 170817. And this was so large because some of these events were only seen with a single gravitational wave detector. So really impressing the need to have a worldwide network to do triangulation. And the distances were 220 and 350 megaparsecs for neutron star black hole systems, respectively. So in the case of GW 190425, this is our second and only other binary neutron star merger that we saw in gravitational waves. The sky area here was actually a quarter of the entire sky, okay, and the distance actually 4 times as far as GW 170817. But impressively, there were certain telescopes and new facilities such as this Wiki Transient facility that were actually able to tile the northern hemisphere part of the sky map within several hours. Now, on the case of GW 190814, an event that also happened in the summer, this was initially classified as a neutron star black hole. Huge amount of excitement as well as telescope time was spent on it. The sky area was actually our smallest localization, 18.5 square degrees, and the distance 6 times that of the original GW 170817. So depth here was a real challenge, but there were many telescopes that were able to actually try to stare deeply and stack images. But the issue here was that this event in subsequent sort of the days following, it was clear that the mass ratio was such that if it was a neutron star black hole, and the question is whether it was actually a neutron star black hole or a binary black hole in the end, was such that the neutron star would have been swallowed entirely whole by its companion black hole. Okay, so there wouldn't have been any expected electromagnetic emission. So I think all of sort of combining our experience from the 2019-2020 run really emphasizes the need for having telescopes that can go deep, that can really be able to do very large areas in terms of sky coverage, that have specific target of opportunity time available to do this kind of science, and as well as really sending out much more accurate and precise information as soon as possible about the events. But I think this will happen as we move into the future, as I'll discuss.
Samaya,
yes.
Sorry to interrupt you. I think you should consider, we are 5 minutes from the end so that we can have some time for...
Oh, okay, sure. Okay, thank you. I didn't realize I was talking so slowly. Okay, but yes, I will. I'll go forward. So in the case of GW 170817, we have this beautiful, beautiful, unprecedented data set. You can see two groups. And what made this so fantastic was essentially that it broadly agreed with the prediction that there should be two types of electromagnetic counterparts, at least, from two different types of matter outflows. So the kilonova, which is this rapid neutron capture nucleosynthesis powered transient, which is thermally emitting in the UVOIR from the hours to days to weeks time scale. And this is essentially coming from these tidal tails or short-lived accretion disk winds, as well as core bounce heating as the two neutron stars slam together and produce this ejector mass and velocity. Or else the second counterpart are these short gamma ray bursts, where you essentially have some centrifugally supported disk powering an ultra-relativistic jet that is slamming into the circummerger density, producing non-thermal and synchrotron radiation. And this detection really depends on where the observer's angle with respect to the barrel of the jet is. And so from the electromagnetic counterpart, we're able to learn a whole host of other information, which I'm listing here. One thing I'd just like to stress is one of the beautiful results that came out from VLBI measurements a year after the event was actually, so this is from the radio, was actually an independent measure of the inclination angle to this structured jet, which showed structure both in energy and the angular and radial side. Okay, and I will return quickly to this in the last 5 minutes. So the task here really is to, and this is where Luciano's group is really leading the charge, is really modeling these outflow microphysics and being able to link these to these electromagnetic counterparts. And there are many, many open questions that remain from this event. How do you form this jet? What is the central engine of the jet? And why was this bright blue flash so bright in the first place? This was somewhat unexpected. So we have this new field where we're combining the gravitational wave data set as well as the electromagnetic data set. There are many degeneracies we have yet to really understand and identify when we're doing this process, as well as really the systematic uncertainties that are coming from, for instance, the electromagnetic counterpart modeling. There, which really have to be incorporated in order to really do this joint analysis. And so in my group, we have got this new, and we're hoping to make this open source. It's been led by my PhD student, this joint gravitational wave and electromagnetic multi-messenger analysis, which is allowing you to really combine the binary properties with the outflow properties using semi-analytical formulae and then connecting these to the observable light curves. Okay, so I'll just give two examples of how this kind of analysis in terms of science can go. So in terms of nuclear physics, what I want to just show here is sort of the first multi-messenger constraints of the equation of state of neutron stars using these two gravitational wave binary neutron star mergers I mentioned, as well as the kilonova measurement, as well as the NICER and other X-ray and radio data sets for two rotationally powered millisecond pulses. Millisecond pulses. And this is also work led by my PhD student in Amsterdam. This is a mass radius plot of for neutron stars. And the purple horseshoe contours here are showing the 50 and 90% confidence regions, and underlined, shown underlined in the color plots are different equation of states, theoretical equations of states. So one can already see that we are able to actually rule out just from these few sources, and this will certain equations of state. And of course, these constraints will dramatically improve as gravitational wave interferometers improve in their sensitivity, as well as we have more nicer measurements as well. Now, in terms of cosmology, I will just stress, because I really think this is a beautiful result. As I mentioned, from the gravitational wave measurement, we have this 1 over distance to the source dependence. And from the optical or any other counterpart measurement, we have the host galaxy redshift. And by using this luminosity distance redshift relationship, we can actually map out the local expansion history of the universe by measuring the Hubble constant. So shown here in blue is the PDF of this H0 constant. Okay, and what you're seeing here in orange and in green were the then 2017 constraints from relative distance ladder measurements using Cepheids and supernova 1As from the Schuss collaboration, as well as the measurements coming from the inferred measurements coming from the Planck satellite from the cosmological microwave background. And what is very interesting over the last decade or so is that the green and the orange results are showing at the moment about a 5 sigma tension in these measurements. And so the hope is that obviously gravitational wave, not from this one event because the posterior is so broad, will be able to actually help us really have an independent method to actually measuring very fundamental quantities such as the Hubble constant. Now, one of the big challenges was actually this distance, luminosity distance, inclination angle degeneracy. This is the yellow banana that you can see here from the gravitational wave sides. And what you see in blue is the constraints using the radio VLBI measurements that I mentioned earlier. So this really allowed us to actually improve just for this one event, this Hubble constant measurement by a factor of 2, which is shown in blue here. What I'd really like to stress here that the caveat here is really in the astrophysical modeling of the jet, and this is why we're really dependent on groups like the Frankfurt group in Luciano's efforts in trying to understand and improve the systematics there to do this. So I'll just end with a few slides on the perspectives. So this first event, the follow-up was very easy. It was very close by and bright, and it had a very small gravitational wave volume. So today we sit here. We've had these previous science runs, these 90 events or so, the only one multi-messenger event. And the huge excitement is that we're about to start a science run next year, which will last for another year. And so what does this mean for us as in the field? Well, with number one, we have to expect a diversity of electromagnetic counterparts. GW17 or 817 is perhaps not representative of every single system. We expect the counterparts to be dependent on the total binary mass, as well as actually what the final object forms. The second is really this challenge, and really for groups like Luciano's, to build this coherent model, really incorporating these huge time steps as well as distances to incorporate the binary evolution to the radio transport to really do this joint gravitational wave and electromagnetic analysis systematically. Thirdly, there are many parts of the jigsaw for this one event that we missed. We did not see any emission from before 11 hours in the UV, for instance, and there's still a lot of open questions as to what it can explain the brightness of the event. And then we are moving already from this individual objects to really this era where we're talking about statistics. So we're here today. I mentioned that we have this next science run. And then we also have our 5th science run. One thing that I've been spending the last year thinking about is what is the science case for what we'll be able to do in this preceding time in the 2030s, before we have our next generation observatories, the Einstein telescope, hopefully built in Europe, as well as the Cosmic Explorer coming online in the US. And so really, the numbers we should be expecting in the next 2 years are sort of tens of these neutron star black holes per year. Fortunately, we have a whole slew of wide field new facilities going online. And in the end of the 2020s, we're talking about tens to hundreds of these events per year. Okay, so it's a real transformational shift. And we also have these fantastic new telescopes actually coming online, such as the Vera Rubin Observatory, as well as the Square Kilometer Array, that are allowing us to actually make not just single snapshots of the universe, but multicolored movies of the dynamic universe. So it's really this combination of having these two facilities that is really allowing us to change this field. And then for the students, particularly in the audience, I really want to stress how exciting the 2030s are with these next generation observatories, where we're looking at a redshift range, as well as probing the source frame mass for the Einstein telescope shown in gray, really reaching sort of tens of redshift, okay? And so GW 170817 is actually off the plot here. It was so close by. So really just to stress how much of the universe we'll be able to observe basically every neutron star, black hole merger. And of course, only even with our most sophisticated telescopes that we expect in the 2030s, can we only follow up just a handful of these events. And we are really looking at there being 10 to the 5 neutron star mergers events happening within a redshift of 0.5 per year. Okay, so this really is just, in terms of the context of the field, it really is a transformational time where we're really thinking not only about how we will follow up single sources and really cherry pick loud events to do sort of very detailed nuclear physics. We'll have very much stronger signals on the gravitational wave side. We'll be able to see their post-merger remnants very clearly because of the high frequency component. But we're also talking about actually cross-correlating all these gravitational wave signals and using them as probes for large-scale structure. So I'll end here now with the fact that I strongly believe gravitational wave and multi-messenger astronomy the future for both are extremely loud and bright. I have focused only on the high frequency end of the gravitational wave spectrum that spans decades in frequency space. There are many other experiments and satellites which are going after many other different sources which will have electromagnetic counterparts. And so I hope, yes, that some of you will be excited and also join this incredibly exciting field and time in the next 10, 20 years. Thank you.
Thank you very much, Samaya. This was really a nice overview. If I was just 20 years younger, I would be so excited now at this point to start wanting to start working with you.
You're still excited, Luciano.
I am still excited, yes.
Yes.
So there are a few questions we should try and address. The first one comes from Amresh Verna, who asks, what are the fundamental differences in gravitational wave features that we detect between binary neutron star mergers and neutron star black hole mergers?
That's a great question. So I had to go very quickly. And actually, this is an area that Luciano has himself worked on. So when we go to these gravitational waveforms, I hope you can see this. One aspect, sorry, I will show you here. So in the case of binary neutron star mergers, this wave strain is shown in red here. And then for black holes, we have this much more vanilla shaped kind of, in spiral merger ring down waveform. So in the case of neutron stars, you can see that the post-merger component actually has quite a lot of structure and individual features. And indeed, work such as Luciano's group has produced has shown that these actually produce a fingerprint of information about not only the final neutron star that was formed, but also the equation of state or the compactness of the actual neutron stars that produced this the final remnant. Now, in the case of neutron star black holes, we expect that the final remnant should actually be a black hole. Yes, so we would expect a much more There would still be some structure during the merger phase, but if the final settling down should be a black hole. So on the gravitational wave side, we will. And at the moment, our main limitation has been that the sensitivity of the gravitational wave detectors has not been sensitive enough at the sort of few hundred hertz to kilohertz regime. But this will surely improve as the detectors improve in their sensitivities. The sensitivity bucket will mean that we will have much more sensitivity to this part of the waveform and be able to do this kind of inference and being able to extract this information. Thank you.
Thank you. So there is another question by Yasmin Mirsi. Thank you so much for this very exciting talk. I was wondering whether we would ever be able to detect gravitational waves from type 2 supernovas. Thanks.
Yes, Yasmin, thank you. Yes, so it's really my last slide. Yes, there's been a lot of work about actually, because, you know, for gravitational wave emission, you need to have this accelerating quadrupole moment. So there has been a lot of work to actually, I hope I have it, to actually simulate core collapse supernova in terms of understanding their gravitational wave emission. And we're still some way away from actually having sort of reliable, I guess, or accurate gravitational waveforms to simulate different types of core collapse supernova. But the hope is that with the next generation observatories, such as the Einstein telescope, there may be the potential to detect them at the moment. At the moment, for LIGO and Virgo, we really have to rely on there being something like Betelgeuse happening. Yes, so it's really about the detection rate or the strength of the signal. I mean, we're really talking about, you know, needing the event to happen or the core collapse supernova to happen very, very nearby. Yes, and so here it's really about the merger rate that we should be able to see. And so in the case of these Einstein telescope, the hope is that there may be one or a couple of these events detectable.
Thank you. Okay, maybe the last, very last question by Alberica, who is a faculty here in Frankfurt. Wouldn't it be wonderful to have a million of those neutron submergers like event produced per second? This is, you know, beyond our best dreams. She says this is indeed what heavy ion collision can produce in accelerators like those at FAIR, which is an accelerator nearby. Which are the measurements we would like to see from heavy ion collisions?
Oh, that's a great question, Alberica. Thank you very much. Yes, so I didn't really discuss, I guess, the overlap with the heavy, I mean, so the information we'll hear from heavy ion collisions, but I know, for instance, the Frankfurt group, you have this wonderful cluster that is actually, you know, combining all the analysis that will happen. And so I think that this is something that there are several groups now working on in terms of what kind of measurements one wants to see from heavy ion collisions, also to probe the QCD phase space. But I'm sorry, I can't be more precise at the moment than that. I'm hoping you will be able to tell me this in the next years.
Okay, well, let's thank again Samaya for this very nice talk. And I'm afraid we have to move. And for this, I need to know from Laura what are the plans. I think we're running a bit late.